Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, find the safest path in a grid. The problem is very interesting and we will also be solving one harder version of this problem wherein grid.length is less than equals to 4000 instead of 400. So if you are here just for the follow-up version, all the timestamps are there in the description down below. Feel free to move back and forth in the video as you like. Having said that, I would encourage you to watch the video till the end so that you can understand the thought process behind the optimizations we are doing, because that's what is important and that's what will help you in solving any future problem that you haven't seen. So with that, let's get started. The problem states that you are given a zero index matrix grid of size n cross n. Each cell will either contain 1 or 0. If it contains 1, then it is a thief cell or it contains a thief. If it contains 0, it is an empty cell. Now you are initially at position 0, 0, and in one move you can move to any adjacent cell in the grid. An adjacent cell is defined as top down, left and right. Now you have the safeness factor of a path is defined as the minimum Manhattan distance from any cell to any thief. Now you have to look at all the paths that starts from 0, 0 and ends at n minus 1, n minus 1. Among all such paths, you have to return the maximum safeness factor, right? So each path will have a safeness factor. From all such paths, you have to return the one which have the maximum safeness factor. So let's take in one example. Let's say this is the grid, and you have to start from 0, 0 and end at n minus 1, n minus 1. There is just one thief here, which is located at 0, 2. Now, let's say this is one of the path, and you have to figure out what is the safeness factor of this path. So, the safeness factor definition was the minimum Manhattan distance from any cell in the path to any thief in the grid, right? So, from this cell, you have to figure out what is the minimum distance between this cell and all the thieves, minimum distance between this cell and all the thieves, minimum distance between this cell and all the thieves, and so on and so forth. And finally, you will take the minimum across all of them. So that will give you minimum across any cell in the path to any thief, right? So it's kind of a n squared thing, right? So let's look at it again. Let's say you have to figure out the safeness factor for this path. So what you will do, you will figure out the minimum Manhattan distance from this cell to any thief in the grid. So what is, there is just one thief here, so Manhattan distance between this cell and a thief cell would be 2. Similarly, minimum Manhattan distance between this cell and a thief cell would be 3, right? And Manhattan distance between this cell and the thief cell would be 4, and similarly this would be 3 and this would be 2. Now each of these 2, 3, 4, 3, 2 is denoting the minimum Manhattan distance from this cell to any thief, but you want from any cell to any thief. So you will just take the minimum across all of them. That will give you the safeness factor of this path. So minimum would be minimum of 2, 3, 4, 3, 2, which will be 2. So the safeness factor of this path would be 2. And you can try out any other possible path. You will see the safeness factor of any other path is not greater than 2, and hence 2 is the maximum safeness factor possible, which means 2 is the answer. So hope the problem statement is clear. Now how to solve this? So let's say this is the grid and the thief cell is denoted by T. Now you take any path, like you have to take all the paths, and among all the paths you have to figure out the safeness factor and then return the one with the maximum safeness factor. So let's say there are p number of paths, right? For each path you will calculate safeness factor. So let's say safeness factor requires some complexity of s, right? And you will just take the minimum across all of them to get the answer. So basically, let's not worry about all the paths right now. Let's see the safeness factor first, because that's what is important. That is what you will be calculating for each of the path. Now what safeness factor is? Minimum across any cell in the path to any thief in the grid. So from this cell to any thief, similarly from this cell to any thief, and so on and so forth. Basically, you want to find out the minimum across all of them, right? So one approach would be to figure out the minimum from this cell to any thief, right? Let's say this number is x1. Similarly, you figure out the minimum distance between this cell and all the thieves. Let's say this is x2. Similarly, you figure out the value for minimum distance between this cell and any other thief is x3, and so on and so forth. So basically, the safeness factor would be the minimum of x1, x2, x3, x4, and finally xn, right? So how you will figure out this xi? Let's say you have to figure out the minimum distance between this cell and any other thief cell. So the simplest algorithm would be just iterate over all the thief cells and figure out the minimum distance between the current cell x comma y to the thief cell r comma c, and just take the minimum across all of them. That will give you the minimum distance between the current cell and any of the thief cell, right? So this algorithm would take order n square time for a single cell, because there can be n square number of thief cells, like all the cells are thief cell in worst case. So this algorithm would take order n square time to just figure out the minimum Manhattan distance between one cell and a thief cell. But for any path, let's say you take this path, you want minimum Manhattan distance between this cell and all the thief, this cell and all the thief, this cell and all the thief, and so on and so forth. So basically, you need this distance for all the cells in the path, and there can be 2n number of cells in a path, right? In best case, so even in best case, it will be 2n cube, right? So let's say what you are doing is you are taking this path, just an example. You're taking this path 2n. So there can be n square number of cells in a path in worst case, and for each cell you require n square time to compute the minimum Manhattan distance between this cell and all the thieves. So finally you will take the minimum across all of them. So this will require order n power 4 complexity to just figure out the safeness factor of a single path. Notice we haven't considered all the paths yet. For a single path, it takes order n power 4, and even that is not possible because n is up to 400. So this we need to optimize this. So basically, we need to come up with a matrix like this, where each number denotes what is the minimum distance between this cell and all the thieves, right? So between the current cell and any of the thief cell, we have to compute this matrix in less than order n power 4 time. We know how to compute it in order n power 4 time. We can apply this algorithm for each cell, and they are n square cells, so we'll take order n power 4 time. But we need to compute in less than order n power 4 time. So this is your new problem now. I would encourage you to pause the video and try to solve this particular problem by yourself. So hope you thought about it. Notice this is very straightforward. We have a thief cell here. So what is the minimum distance between the thief cell and that cell itself? So basically, minimum distance between this cell and any of the thief cell. It will be 0, right? Because this cell itself contains the thief cell. So minimum distance would be 0 here. Similarly, distance would be 0 here, and similarly distance would be 0 here, right? So let's get rid of this, and similarly distance would be 0 here. Now what's next? You can calculate, or you can say deterministically. You can deterministically say that this value would be 1. The minimum distance would be 1 here. Why? Because this is adjacent to this, right? And this value is 0. So this value will be at least 1 for sure, right? So similarly, this will be 1, 1, 1, 1, 1. So basically, you are able to figure out the minimum Manhattan distance between this and all of its neighbor. Now in the next iteration, you can figure out the distance between this and all of the neighbors. So if you think about it, if you visualize it, what's happening is initially there are some cells which have 0, then you figure out some cells which have 1, and then you figure out some cells which are the neighbors of these cells as the Manhattan distance of 2. So basically, you are doing a BFS in a sense, right? So that's what we will be doing. We will simply initialize our BFS queue initially with all the cells which contains the thief. So 0, 2 contains the thief, 0, 4 contains the thief, 2, 3 contains the thief, and 4, 0 contains the thief. So we just put all of them into our queue and we mark their distance as 0, right? Now we will just pop everything one by one, just like normal BFS. We'll pop this and visit all its neighbors. So the neighbor of this is this, and this. So you will just mark these things as 1 and push these to the grid as well. So basically you will push 0 comma 1, and you will push 0 comma 3, and finally you will push 1 comma 2 as well, right? So after you do this, you will pop the next element, which is 0 comma 4. So again 0 comma 4 neighbor is this and this is already visited, so you will not consider this, you will take this one. So again you will push this to the queue, and you will keep on doing this and entirely, and until the entire grid is full or the queue is empty. So this is how the algorithm will proceed. Initially you have these all neighbors, so you mark this with 1, and these are, notice that these all are already visited, so you will not visit any of these again. Now after that you will visit all their neighbors, so these are the neighbors, right? So you will visit all of these, and finally you will, and notice that these cells are already visited, so you will not cover these cells at all, right? So all of these are already visited. Now finally you will, this is also visited, you will just visit these 2 cells, and this will be 3. So at the end of this entire BFS, you will be having this particular grid. So what you are doing, we are simply doing a BFS, so we are visiting each cell exactly once, or in other words at most 4 times. Basically for each cell you will visiting all its neighbors. So a single cell can have 4 neighbors, so it can be visited from 4 directions. So the overall complexity would be 4n square to get to this matrix. Notice initially we, in brute force manner, it was n power 4, but now we have brought down to 4n square by just doing a simple BFS. Now we have figured out this value. Now for a single path, what is the safeness factor? Safeness factor would just be the minimum across all the nodes in that path, right? And that will be a safeness factor. So for this particular path, safeness factor would be the minimum of 2 3 2 2 2 2 2 2 3. So minimum, the safeness factor of this particular path would be 2, right? So now you are able to figure out the safeness factor in just order n time, or basically order p time, which is p is the number of or let's say order c time, where c is the number of cells in the given path, right? Now notice you have to do this for all the path p. How many path p are possible? It will be exponential. So here we have all the possibilities. You can go up, down, left, and right. But if let's say if you have possibility of only going left and right, which is which is more restrictive, even then the number of paths would be of the order 2n cn, which is exponential. So you can't actually iterate over all the paths, right? And still you need to figure out the maximum safeness factor, right? So think about it. We need to figure out the maximum safeness factor without iterating over all the paths. So what is the maximum safeness factor possible? It is 3. Why? Because you consider any path, and what you will be doing finally, you will be actually taking the minimum across whatever cells you have considered. So maximum value of any cell here is 3. So maximum safeness factor that is possible is also 3. So what you can say, okay, can I get a maximum safeness factor of 3? If the answer is yes, then 3 is the answer, right? If answer is no, then you will say, okay, can I get a maximum safeness factor of 2? If the answer is yes, then 2 is the answer. If it is not possible to get a maximum safeness factor of 2, then this is not the answer. Then you will try 1. Can you get a maximum safeness factor of 1? If yes, this 1 is the answer. If not, then you will try out 0, and 0 will definitely be the case, because basically you are saying that you can go to the thief cell as well, so you will finally get return 0 as the result. So hope this new algorithm now makes sense. What the new algorithm is, instead of iterating over all the paths, you are now iterating over the maximum safeness factor one by one, and you are trying to figure out whether a given safeness factor is possible or not. So how to figure out whether a given safeness factor of x is possible or not. This is a very standard problem. Given that, given a grid, you need to figure out what is the safeness fact, what is the whether a path exists which have a safeness factor of x or not. Now, why is this standard? Because you can think of, let's say you have to figure out whether a safeness factor of 2 is possible or not. So basically, it means you can only visit these cells. You can't visit any other cells. All the cells are, if you visit, you will not get, 2 will not be the answer. So you can only visit these cells. Now you have to figure out whether it is possible or not. So I would strongly encourage you to pause right away and try to solve this particular problem by yourself, because this is a very standard problem. Given a grid, you can visit some of the cells, and you have to figure out whether it is possible, whether a path is possible from 0, 0 to n minus 1, n minus 1. So hope you have thought about it. I think this picture itself might have made it clear. Let's say you have to figure out whether safeness factor of 3 is possible or not. So what does it mean? It means you can only visit those cells which have value greater than equals to 3, right? You can't visit any cell which have value less than equals to 3, which have value less than 3, because if you visit any cell which have value less than 3, the minimum across all the cells in the path would then be that minimum value, right? So you will only visit the cells which have value greater than equals to 3. So you can only visit these 2 cells. So in other words, all other cells are blocked. Now what you need to figure out, we need to figure out whether there is a path starting from here and ending at here. So can't you do this? You can do a simple BFS, right, to figure out whether it is possible to reach from this cell to this cell without actually visiting any of the blocked cells. So if the answer is yes, you can say 3 is the answer, right? If it is no, you will try out the next possible next possible greatest safeness factor, which is 2. So again you will say, okay, for 2, I will visit only the cells which have, or I can visit only the cells which have value greater than equals to 2. So you can't visit any of these cells. Now you need to figure out whether there is a path possible starting from here and ending it here. If there is just one path, even just one path possible, then it is possible to get a safeness factor of 2. So you can simply do a BFS again, or a DFS, whatever you want, and figure out whether there is a path or not. So in this particular case, there is a path. So D equals to 2 is a valid candidate, or basically you can get a safeness factor of 2, and hence 2 will be your result for this particular sample case. So what is the overall complexity now? So what we are doing, we are simply iterating over all the results starting from 400 to 0, or in other words n to 0, because n is the maximum distance possible in the grid. So you will try everything from n to 0. Why n to 0? Because you want maximum value. So you will try the maximum one first. If it is satisfied, then this is the answer. If it is not satisfied, then you will try n minus 1. If this is satisfied, this is the answer. Otherwise, you will try n minus 2, and so on and so forth. So you will try out everything. For every case, what you are doing, you are preparing a new grid where each cell is either black or white. You will mark every smaller cell as black, and you will prepare this new grid. Now once this new grid is there, you can simply check whether you can reach n minus 1, n minus 1 from 0, 0 or not. If you are able to reach, this is the result. You will return this particular value as the result. Otherwise, you will try out the next smaller safeness factor, right? So what is the overall time complexity of this entire algorithm? This calculated distance was taking you order n square time. We have discussed this already. This was just a simple BFS. Now inside this, what we are doing an order n, we are doing something n number of times. Now what we are doing n number of times, we are preparing a new grid that will take you order n square time, right, to prepare the new grid. Basically you just have to check whether the value is greater than equals to the given result or not. If it is, you will simply mark it as white, otherwise mark it as black. and then you have to check whether it is reachable or not. So that will also take you order n square time. Basically, you will do a simple BFS or DFS to figure that out. So in total, this entire piece will take you order n cube time. N cube plus n square, which will boil down to order n cube. So this is the entire complexity of this entire algorithm is order n cube. So in order n cube, you are able to solve this problem. N cube should have been passed, but as you already know, Leetcode is famous for very bad or very impractical time constraint. So n cube will not pass here for sure. So basically, you have to optimize this further. Now, which of these factors you can optimize? This n square is okay with us. You don't need to worry about this n square thing at all now. N square will surely be within the constraint. Now, inside this, for a single cell, for a single candidate, you are doing some order n square operation. Now, either you reduce the number of candidates or you reduce the number of operations. So reducing number of operation itself is very hard, right? Because this, if you don't prepare this black and white grid, how will you figure out whether it is whether a particular result is reachable or not? So one thing you can see is we are searching for result in a linear fashion. We try we try n minus 1, then we try n minus 2, n minus 3, and so on and so forth. So whenever you see this kind of thing, just see if binary search is applicable or not. If binary search is applicable, you can simply reduce this for loop from order n to order logN. So this factor would be replaced from order n to order logN, and this entire thing would become n square logN, which will pass the given time constraint. So let's see if binary search is applicable or not. So if you are new to binary search, there's already a video I've recorded. I would encourage you to check that out to understand how to see if binary search is applicable or not. In short, you have some sample space. You have to figure out which is the result. Now the function should be a step function kind of thing. So basically, if at any point, if you are able to deterministically say whether you will go left or right, not in both the direction, then you can apply binary search. So in other words, in this particular scenario, we are saying whether, let's say, x, a safeness factor of x is possible or not. So if the result is okay, like safeness factor of x is possible, then you know that safeness factor of everything less than x is also possible. Why? Because safeness factor, let's say safeness factor of 2 is possible. So if safeness factor of 2 is possible, what you will be doing for safeness factor of 1? You will mark some of this cell as white cell. Whatever white cell already existed, you don't touch them, right? You will just add extra white cells. So basically, if this cell was reachable, like if these two cells were reachable from each other previously in d equals to 2 itself, it will be reachable in d equals to 1 as well, right? Because you are not removing any of the existing white cells, you are adding white cells, right? So if x is true, or in other words, if we are saying that safeness factor of x is possible, then safeness factor of everything less than equals to x is possible. So what you will do, you will only search in the right half. You will say, I will try to see whether a safeness factor of greater than x is possible or not. If let's say the answer is false, in that case, let's talk about this. Let's say answer is false in this, like in this scenario. So will it make sense to check for any of the things in the right? D equals to 3 is false. If you try d equals to 4, if you prepare the matrix for d equals to 4, some of this white cell will also go away, right? If they are not reachable, if 0, 0 and n minus 1, n minus 1 are not reachable in d equals to 3 itself, if you remove some more cells, how will that be reachable? So if x is false, you can simply say I will skip the right half and I will only search in the left half, right? So for a given point, we are deterministically able to say whether to go left and right, and hence binary search is applicable here. So we can simply replace this linear for loop with a binary search, and this entire thing would stay as it is. So we will, for a single x, we'll figure out whether it is yes or no with this particular algorithm, which will take us order n square time, and we will do binary search. We will ask this question login number of times. So in total, this algorithm will be reduced to n square log n from n cube, and this will pass the given time constraint. Again, depending on how you implement it, but this should pass the given time constraint. So let's look at the code. Again, I would strongly encourage you to pause the video right away, try to code this entire thing and get it submitted by yourself as well. If not submitted, at least try to make sure that you are able to pass first 1000 test case. Like there are, like, I think some 1300 test cases or so, if I remember correctly. You just make sure that you are able to pass at least 1000 test cases, so that you can, you know, your algorithm works. So next we're looking at the code. So again, hope you have tried this entire thing by yourself first before you are jumping here. So this is the code. The code is very straightforward. We are doing binary search over the result, and for each one we just check whether m plus 1 is valid or not. If it is valid, we will search in the right half. If it is not valid, we will search in the left half, right? Now, what is valid function doing? Is valid function is again very straightforward. If you remember, we had to do this two things. We will just prepare this black and white cells, and then we will simply do a DFS. Now I am not preparing this black and white cell explicitly. I am just making I am just keeping track of what is the value there, and seeing whether I am allowed to go in a different cell or not. So basically, if the distance of 0 comma 0 is itself less than max distance, it means this cell is the initial cell is itself black, so you can't do anything, you have to return false. Otherwise, you will push the initial cell and you will maintain the visited array. Initially 0 comma 0 is visited. You will do the BFS. In BFS, if you encountered n minus 1 comma n minus 1, you will simply return true, because it says that you are able to reach from 0 comma 0 to n minus 1 comma n minus 1. So there is a path, so you will return true. Otherwise, you will visit all the neighbors. For each neighbor, you will see if it is already visited. If it is not visited, you will visit it and see if you are allowed to move there or not. So basically, whether the new cell is a black cell or a white cell. If it is a black cell, you can't do anything, you will simply continue. Otherwise, you will push it to the queue because it is a white cell, right? So this entire thing will run in order n square time and will give us whether a particular thing is valid or not. And we will, as we have seen, we are doing this login number of times inside this binary search loop. So entire complexity is order n log n. Now one last thing is distance to every node. This is also very straightforward. As we have discussed, what we will be doing, we will simply insert everything with 0 initially. So that's what we are doing. We are simply inserting everything which have a thief with a distance of 0. After that, we are popping the queue one by one and visiting all these neighbors. If it is visited, we will simply continue. If it is not visited, we will visit it, and the distance would be distance of parent plus 1, right? So hope this entire solution makes sense. If you have any doubts in this particular piece, feel free to post them in the comment section below. I would be happy to answer. Now comes the interesting part. Let's say the constraint is not 400, rather it is 4000. So in that case, even n square log n would not pass for sure, right? Now how to solve this? Basically, you have to either remove one of the n from here, or you have to remove log n from here. So let's see how to solve this. So notice this was something we were doing. We initially started with 4, right? Let's say we prepared the black and white matrix for 4, then we prepared the black and white matrix for 3, we prepared it for 2, and then we prepared it for 1, right? And finally we prepared for 0, where everything will be white, right? Now think about it. What's happening here? What we need to find out? We need to find out whether there is a path from 0 comma 0 to n minus 1 comma n minus 1, right? So in other words, if you look at it closely, what's happening is, in each iteration we are merging some of the white cells. So initially there were these two sets, then we merged everything here, right? And then we merged some more white cells, right? So basically in every iteration we are merging some white cells, and finally we need to just check whether this 0 comma 0 and n minus 1 comma n minus 1 belong to the same component or not, right? So hope you are getting the intuition. Basically this is very straightforward disjoint set union problem. You are initially given everything is initially empty, or basically everyone is in their own group, right? Now after every iteration you are merging some of the groups, and if at any iteration group 0 and group n minus 1 n minus 1, if they are both in the same group or same component, that will be your answer. The first time it will happen, that will be your answer. So in this particular case, this is the first time where this and this cell are in the same group, and hence 2 is the answer, right? So what we will do, we will simply start we will simply do a DSU. We will keep every cell as their own independent cell, and we will simply keep on iterating the result. So let's say initially we pick 4, so 4 everything is black. Now we go to 3. So when we go to 3, we know that this cell is now become active and this cell is now become active. So if these two cells are active, we can basically visit any of their neighbors. So basically we can merge this cell with any of the active neighbors. So if this neighbor is active, we can merge these two cells. If this neighbor is active, we can merge these two cells. If this neighbor is active, we can merge these two cells, right? But in this particular case, there is no active neighbor, so this cell is still on its own, and even this cell is still on its own. Now when 2 comes, you know there are some more active cells found, so let's quickly go over them. So this was the 2 groups which were found previously. Now you got one more active cell. Now as soon as you got one more active cell, you will visit all its neighbor or all its active neighbors. So there are 2 neighbors, 1 and 2. This is not active, so you will not merge these 2 cells, but this part is active, so you can merge these 2 cells, right? And similarly, this is new active, you will again visit all its neighbors and merge the active neighbors, and so on and so forth. So you will keep on doing this, and finally you will be getting all of these merged into a single component. Now after this entire thing is done, or after you have iterated over all the 2's, you can simply check whether 0 comma 0 and n minus 1 comma n minus 1 are in the same group or not. If they are in the same group, 2 is the answer. If they are not, you will try out the next possible smaller value, and you will keep on doing this until they are in the same group. And at 0, it is certain that they will be in the same group because everything will be white. So they will be in the same group for sure. So hope this entire solution makes sense as well. So the new pseudo code would look something like this. Basically, we are still calculating the distance array because that's what is required for figuring out black and white thing. Now notice we have to iterate over the cells in their order of distances. So we will first iterate over all the cells with distance 3, then we will iterate over all the cells with distance 2 and 1, and so on and so forth. So now we maintained a simple unordered map where each cell we maintained what is the number of cells which have this particular distance. Now we will simply iterate starting from 400 to 0 because 400 can be the maximum, or 4000, sorry, because the new constraint is 4000. So 4000 can be the maximum result possible, or maximum safeness factor possible. So we'll iterate from 4000 to 0, and we will see what all cells have 4000 value. So we will activate all of them. So we will simply iterate over them, activate them, and then visit their neighbors. And if the neighbor is also activated, then you will simply merge this cell and the neighbor cell, right? You will, after you have done this entire thing for complete cells, you will simply check whether the leader of 0 comma 0 is equals to leader of n minus 1 comma n minus 1. If they are equal, that will be the result, right? So again, I would strongly encourage you to pause and try to code this entire thing by yourself. If you don't know about DSU, these 3 are the DSU functions: merge, merge and leader. These 2 are the DSU function. I have written a DSU class already, so you can simply copy paste this and then try to code this entire thing by yourself. You don't know DSU should not be excuse for coding this entire thing by yourself. So just take this DSU class and try to code the remaining thing by yourself. So hope you have tried at least this by yourself once. Next we'll be looking at the code. The code is again starts with finding out the distance, as we have discussed. So distance, we will be using the same function that we have discussed previously while discussing the binary search approach, and then we will figure out the cell and distance piece. So here we have maintained a map to just make sure that this is order n, but here I have just sorted it, but you can just simply replace this with a map, and this will be this login factor that is coming because of this will also be removed. So that was my bad, but basically you get the idea. You can sort this without actually doing a actual sort, because only 4000 values are there. So you can simply maintain an array of 4000, and each array will have an array of cells which contain that values, right? So once you have this, we will simply declare DSU and then maintain the active cells as well. Now, as discussed, we will iterate from n to 0, and we will keep merging. So we will iterate over all of the indexes which have the value result. So this while loop is there just instead of this for loop, because of how I have sorted it. If we have maintained a map, this while loop would be simply a for loop. Now inside this, as we discussed, we'll simply activate the current cell, and then we will visit all its neighbors. If the neighbor is valid and it is also activated, we will simply merge the current cell, the current neighbor and this current cell. And finally, after we have done this for all the indexes with result value, we will simply check whether the leader of 0 is equal to leader of n square minus 1. If they are, we will return this particular result. Otherwise, we will try the next smaller safeness factor. So hope this entire thing is clear. One small thing, this DSU, to make this DSU work, because this is a grid, right? We have simply converted this grid into a linear array. We have assigned one ID to each of these cells. So this is 0, this is 1, this is 2, 3, 4, 5, 6, 7, 8, and so on and so forth. So basically, that ID is something which is assigned through this value function, which is simply assigning the ID to R cross n plus C, right? So hope this entire solution makes sense. So this entire solution complexity would simply replace this login factor as well, because we are not doing any binary search or any kind of sorting. We are just simply doing a merge operations, and that will take an amortized complexity of order n. So any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.